down on that, please? You can see this a little better. Okay, so this is the one that had the issue, right? Or have I fixed the issue now in this one? Oh, this is the one that breaks. Okay, yeah. So let's walk through this. So let me run it here first. So I'll go run, and then I think the number. What was the number we were? Yeah, we were doing -2, and then we decided 16 bits, or we were doing 4 bits. 16. All right. So so that one finished. I thought it was -2 and 4. Yeah. It's definitely broken. Here, we'll just do 64. That should definitely work. It's funny. It's giving us a lot more space now. All right. Well, we'll talk about it anyways. And I think we can still show, because it was not showing. I was getting an answer, but the wrong answer when I ran it locally. And we were getting a segmentation fault here, so maybe we're running on the other server, the one that doesn't require prototyping or something like that right now. But here's the issue. When we say that we're going to represent this value as a 8-bit value, let's say, 8 bits would be 8 zeros or 1s, correct? Well, we decided to represent our bits just haphazardly. We said, oh, doesn't matter about how much memory it takes, blah, blah, blah. We're going to represent our bits as ints. So even though we only need a single bit, a single 0 or a single 1, we're actually allocating 32 bits to hold our single 0 or our single 1. All right, so when I say give me enough memory for 16 bits, that's going to give me 16 bits of memory. 2 bytes of memory, right? One integer is 32 bits. All right? So, and what we're implying here is if we're going to represent this thing as 16 bits, we need 16 integers, right? 16 integers is 16 times 32 for 512 total bits. That's how much space I really needed to ask for in this case. Okay, but I didn't. I asked for 16 bits. Nowhere near enough. And then I'm just hopping through memory, these giant 32-bit steps. So after my very first, I was only able to store the first half of the first number in memory that I requested. After that, I'm playing with house money, just traipsing through memory. That makes sense? All right, so, and that's actually why I think we're getting all zeros here for this answer, because it's printing out memory differently. So let me kind of show you in an alternate program here.
This is not the program.
This isn't the one?
Yeah, this is just a decimal divider.
What was our program?
Yeah, that one. No.
Oh, but I put it on Slack, right? So we will just bring it back.
Have you literally just like emailed the guy who asked for his website looking or something?
That doesn't matter. Because I would just rate it locally. All right, why is this broken? All right, so we'll just dump all this, replace it with, oh, that's weird. Dump all that, replace it with that. Okay. So Control S to save on this one. run -2, 16. Okay, there's our malloc issue. All right, so what we need to do here we're asking the question, so we're using 2's complement to encode our values that are less than 0, right? Otherwise, we're just storing it normally, all right? But we have to know that the value is stored in 2's complement form, so we look at the leading number, and if it's a 1, that means it's a positive or a negative number, and if it's a 0, that means it's a positive number. So 0 means we don't have to decode it, but we did give up one of those bits for storing the value. A 1 means that it's a negative number, we have to decode it. So we have to turn it from 2's complement back into its negative equivalent. Okay, so this is where we're doing that negative stuff. All right, so reading our value here. How many bits here? We're okay there. If it's less than 0, we're multiplying our value by -1 to give us our positive version of that guy. Then we're going to get the answer, which is going to be an integer pointer that's going to be returned from decimal to binary. Okay, so we'll pass value in bits into that. So that's decimal to binary down here. Okay, so here's our first place where we have a problem. So we have an int pointer answer. We have an int pointer answer, and we're allocating only enough memory for the number of bits. We need times size of int. And what's really funny about this is historically, I'm very verbose. I always explicitly say this, but for some reason, we were talking last time that we didn't need to take the steps of the same size, so we took it out there, and then I must have also taken it out here. But in any case, now we're requesting enough total memory. This is how many bits I'm storing. I happen to be representing my bits as integers. Give me enough RAM, give me enough memory to hold that amount of stuff. All right, similarly, so that should then do decimal to binary just fine. The rest of this is just normal decimal to binary syntax. So then back up here, we'll go ahead and call print array, passing it the number of bits. Print array takes in, so we're going to go through here, and we're doing, here's the AR plus I. This is what we did last time, where that's correct. That's taking the correct size steps through memory. Where I used to say times size of int, which would make it a double step in this case. Actually bigger than that. Way bigger than that. Okay, so print array should be fine. Then we're going to get our binary to 2's complement. So we're going to go and fix our code in that. So that's this dude. Same exact problem here. We need to request enough RAM, enough memory in order to do this. So we need to say times size of int because we've chosen to represent our bits as ints, which is memory inefficient, but at the very least we should ask for enough memory. All right, and we also need to do it down here for our 2's complement. So we were doing 1's complement first, then we were doing 2's complement. So this is bits times size of int. Now, we actually didn't need answer 2 originally, but that was what we were trying to debug it and fix it. So for right now, we'll just we'll go ahead and give that guy enough memory, and it should just still work. Size of int. So the first thing we do is we get the 1's complement, so we flip all the bits. Then the 2's complement, we add 1 to that guy. And this is where we're building our answer 2 in that. Ultimately, we make answer 2 point to, well, answer 2 at an offset point to temp. So we save this, we run it, -2, 16, and then we get an answer. Make sense? All right, so the issue was we were not giving us enough memory to even store one of our bits, let alone 16 of them, because our bits were represented as 32-bit values. All right, so that's 2's complement stuff. Now let's get into the book here. Did your iBook finally start working?
Yeah. So weird. Like for a couple days it wasn't working.
That is strange.
That evening I tried it again. Yeah.
Did you have the same problem? I wonder. Was it just here on was it here on campus?
Yeah. I know, like internet was down, but I was getting everything else fine.
Yeah, but I mean I had a similar issue like earlier today. Internet seemed to be just fine, but I couldn't hit GitHub.
Really?
Yeah, on campus. I was down in the lab there. I couldn't hit it on the wired network, couldn't hit it on Falcon Net. I ended up sharing the Wi-Fi sharing my cell phone network, and it worked fine then.
Really?
But I could hit Blackboard, I could hit Google. Yeah, so something weird must have been going on maybe with their DNS server. But you could get to Zybook's site.
Yeah, like I got to the site, but as soon as I got into the book, it like said cannot connect to the server.
Huh. Well, that would probably be a different, yeah, so this is learn.zybooks.com. Maybe it was this that wasn't, the DNS server wasn't resolving.
Yeah, maybe.
Interesting. Okay, so I think what, here can I do this? Yeah, that'll show me, tell me how far you guys have gone. All right, so I had you go through.
2.7.
Okay. Yep, so it looks like pretty much everybody did that. Not a lot have done 2.3, but oh, I see. You just skipped it. Yeah, it would make sense to kind of do it. So then the question is, who is the one who who's the one person who did it?
Yeah.
No, I just want to see. Then I thought like if you see there and you did not give an item, so I just read everything but did not do that.
I am the one who do it.
You did it? She said she did it. You did it too? Is two people out of, we got 5, 6? That's not 19%.
I think she got
started, but
she
I
did.
didn't finish.
I started, not the complete. Yeah, maybe
I too started.
answer all the.
I completed 3%.
Let's see about, we're checking Van here.
2.4, I got it.
Oh, he does. He did 2.3. All right. Terrible. All right. All right. So let's keep trucking. We've pretty much actually talked about the stuff that's in 2.3 already, right? I think we actually went through it in class. So that's not the end of the world. We talked about signed and unsigned numbers last time. We started talking, so I had you do 2.4, which we had already talked about, but I had you go through that, right?
Mhm.
And then 2, 5, 6, and 7? Okay. All right, so everything's short of procedures. Good. Yeah, that makes sense. That's where I was wanting to go today. So I'm not going to do anything with assigned, unsigned. I think we've beaten that to death at this point. All right, so we're good with two's complement stuff. All right, so representing instructions in the computer. And this is going to be, I think, some interesting stuff we're going to talk about today. And we're going to be able to skip a lot of it because we've already done a lot of the conversion stuff. But I really want to spend some time talking about address spaces and think about how ARM is actually written. And then I have an idea for something I want to maybe do as a development exercise, but let's see how things are going when we get to that point, because it might be kind of difficult, but I like giving difficult assignments. So that might be fun, right? Well, I didn't give you a hard assignment last week, so now I owe you.
Oh no, come on.
I mean, we couldn't figure out last week.
I know, I felt so stupid.
So hard, you could.
No, actually, here's the really funny thing. Because you emailed me the next morning, right? Or did you email me that night? Yeah. I want to say, because I had figured it out before you emailed me. but it was because I think you emailed me like at 2 or 3 in the morning, right?
No.
Yeah, late night.
It was late.
11, something.
Okay. I'm trying to think when I figured it because I thought I was sleeping.
When you figured it out.
And, I dreamed like, oh my God. I woke up like, oh, come on. But then I saw his email, so I forwarded it to the group and, said that he's the one who figured it out. And he was, he emailed me before I emailed everybody else. So, but yeah, it did
I
a,
figured it out before I got home.
before you got home. So
Yeah.
you figured it out before him.
I don't know. I drive in the car and I think we need to put some side bit because before that you have side bit on the.
Yeah, but did you know why? That's the
Yeah.
thing. It can't just be because we did it before.
Well, I usually think of the C sharp and C different thing, but we have to give enough for memory.
Yeah.
So the bit is only not given enough for the 30, 32, 16 bit for
I mean, because like what we effectively did is we tried to, like for instance, I wear a size 4X shirt. All right, so we decide, okay, I need a 4X. So then I went to Kohl's and I went to like the newborn infants section. I got one of the little tiny little shirts for like a brand new baby, and we tried to put me in that. Except this was worse. What we did.
And I know that you have to put the side bit on every, the bit that you put it in. I think in the class I already have the idea in the class, but I don't know right and wrong.
Yeah.
The thing right on
I
the
was
bit.
checking the loop in the class. I was not seeing what is in the
Yeah, we were just so far in, we just weren't seeing it.
I know we were over 90 somewhere, but I was seeing the loop. Something wrong with the loop.
Yeah.
Then when I got home, I tried to fit the side bit in, and I forgot one side bit on the first column. I put something silly, and it doesn't work. And after that, I got the Slack from you saying marketing. I thought you emailed to develop the website. I don't even know who's marketing.
Oh, because I said his name.
Yeah, I don't even know marketing. I thought you emailed.
Well, I mean, hey, that is a reasonable assessment. Chances are the maker of the website is some foreign guy. So one foreign name's just as good as another one, really.
I seriously, I don't know what marketing is. I know
That is his name.
the first name.
I wanted to pronounce it quick, right?
I can pronounce his
He
name.
can't pronounce anything the right way.
I know his name is the on the first name or something. I can't pronounce.
I don't think he can pronounce my name. Say my first name.
Who?
My first name.
Littman.
That's my last name, Michael.
Yeah.
That's actually that's not too bad.
Yeah.
Only my mom calls me Michael though.
Hello.
Yeah, it's only Michael when I'm in trouble.
I don't know. You say my.
I go by Mike most of the time.
Yeah, but you put in there manic on
Yeah.
on Slack. I thought you emailed.
Yeah, I understand what you're saying. Yeah, or maybe I just made up a foreign name. Just banged on the keyboard. That's what came out.
Automatic. Correct.
Yes, that was the autocorrect. Okay, so let's look at now. We've already talked about this a little bit, but in order to kind of keep the number of instructions down, the book has invented this language called lag V8, which is a subset of ARM. So we're dealing with a real instruction set here called the ARM instruction set, which is found in a lot of mobile devices. So anybody in here who has a smartphone has an ARM processor in it, or something very similar to it. I mean, Android phone, you definitely have an ARM processor. To be honest, I'm not 100% sure if Apple's processors use the ARM instruction set. I suspect they do. That's actually a very interesting question. They're definitely a reduced instruction set chipset, a RISC chipset. So let's see. Apple, what's the current chip? The A8? A11.
11.
A11.
Yeah.
A11 Bionic. Electronic. Just say ARM. 64-bit ARM-based system on a chip. Okay. Yeah. So, I mean, so keep in mind that ARM is a common instruction set for reduced instruction set systems. Now, what's kind of interesting here, when I say, let me go back here. When I say RISC, that's reduced instruction set. So this is reduced instruction set. Is this something new? Because it seems like, so our Intel-based processors, so on our laptops and our desktops, these guys are not running reduced instruction sets. These are running full-size instruction sets because you don't need to miniaturize things and stuff like that. That's been around for a while. But it seems like all of our mobile devices are all running RISC-based processors, ARM-based processors. So ARM kind of becoming the popular instruction set, and it happens to be an example of a reduced instruction set architecture. That's what ARM is, an example of that. So is this idea of a reduced instruction set, is that new? Or has that been around for a while? What do you suspect?
It's been around. Wouldn't they like need that to make things smaller quicker?
Well, possibly. That's actually not a bad approach. So if we go back to kind of the earlier days of computing, you know, they may have been looking for ways of allowing processors to do more with less. So, you know, when you have an instruction set, each of those instructions is represented in hardware, right? So you have some little program created in hardware that lives on the chip, lives on the processor. Now today we can fit a whole bunch of stuff on our processors. Not an infinite number of stuff, but we can fit way more stuff on a processor today than we could in the late 90s, early 2000s, or even 3 years ago, let's say. Okay, so in the early days we might have had a reason to say, okay, well, we can only fit so much stuff on this processor. If we can reduce the number of hardware-based magic tricks we need to write, that might save us some space and maybe be able to give us either a little bit more horsepower or maybe be a little bit easier on the heat. Okay? Now, there was actually a pretty famous reduced instruction set processor from the let's call it the 90s, even early 2000s. Anybody know the name of the processor? It used to run on Apple computers. Apple uses Intel processors today, right? They have not always used Intel processors. In fact, Apple didn't switch to Intel processors until after Steve Jobs came back to the company. And after the second version of Mac OS X? I think at least the first version, possibly the first two versions of Mac OS X were written for this processor, not for Intel. Anybody know what the name of the chip was? Well, yeah. Apple had the G3 and the G4 processors. So that's kind of like saying Intel Core i7. The G3 is like the i7. So the actual chip was called the PowerPC chip. Okay, PowerPC chip. And this was a reduced instruction set chip. Examples of this would have been the G3, G4. And they were popular, especially among Apple fanboys. They thought they had the best chips in the world. And actually a very interesting thing, there's a website, I maybe have referenced it in here before, called distributed.net. I talked about that in here last time, I think. So I used to use that. My buddies and I, when we were in school, we would, see who could crack the most codes and stuff like that. So when I had one of my hobbies was I had a Linux machine, I had a Windows machine, I had a Solaris machine, I had a Mac, and I would get them all working together, talking to each other, networking type stuff. So I had a G4 Mac, And the G4 Mac had a technology in it called Altivec. I think I'm spelling that right. And Altivec was kind of like hyper-threading, what's in our Intel processors now. So kind of a way of kind of queuing up extra instructions, but it was way before hyper-threading had come out. So that G4 processor, gave me major street cred when it came to distributed.NET, because I was processing a lot of keys because of that with a G4 processor. Now, the issue here, though, is early RISC processors did not take off due to production issues. Now, we did have some other processors that were RISC-based that did well, but they were in a much smaller group. So, for instance, Sun Microsystems used to have, they had a RISC processor. Anybody know what their RISC processor was called? Spark chip. All right, and if you some microsystems, so some workstations don't even exist anymore, I guess, because now it's Oracle. But if even up till not that long ago, you could still go online and buy a Sun Spark station that had a Spark infrastructure on it. But Sun Microsystems also made their operating system, which is called Solaris, for Intel, to get people to start dabbling in Solaris, because that was when the Linux was making their big push to think they could replace Windows. In fact, Walmart used to sell computers, like low-cost computers that were running a Linux distribution called Windows. Ever heard of that one before? So it was Linux. That way, the cost of the machine would be less because they didn't have to pay the license to Microsoft. But it looked a lot like Windows, but that didn't do very well. So then we have another one, and the book actually references this one, a processor called the MIPS processor. These are all reduced instruction set processors. Now, what's interesting here is arguably, you could say that Apple, well, let's just do this, Apple and PowerPC. We could say Apple did not become the Apple we know today until they dropped PowerPC for the Intel architecture. And that was really a major risk for Apple. And this is related to what we're talking about here, because at that point in time, so when they got rid of the PowerPC architecture, this is after they had already just gone through a pretty tough time. So if we kind of roll back a little bit, we think, so Apple had OS 9. All right, that was their flagship operating system. And we're going to say OS 9 was buggy and we'll just say crashed a lot, something like that. So, and this is during that time period, actually a little bit before this, is when Steve Jobs was acquired by Apple, brought back with Next Computers to Apple. So that's when they released OS X. Okay, you can think of it as OS. So the big question mark is the X for 10, or is it the X in Unix? Which did the X stand for? Who knows? I think Steve Jobs has said 10. It stood for 10, but it's at least an interesting, question to ask. But the original OS X ran on PowerPC. Actually, let me put this underneath here, because there's, Apple. It's very interesting to look at Apple today and realize, and it's kind of amazing that they survived. Because they have two issues here. So the original OS X, which is what we have today. I mean, right now we're running OS X, 10.11 or something like that? 10.13. This is the 13th version of Mac OS X. It's been around for a while. Figure a version came out every year ish. Got a couple of skips in there, but so you're probably talking 16 years, 17 years. Yeah, actually, first version might have been around 2000. It's probably pretty close, probably right around then. So these guys ran on PowerPC, but now what you did is you switched the operating system. So OS 9 was Apple's previous operating system, right? OS X was a brand new operating system based on Unix, based on Linux. Actually, it was based on OpenBSD Unix, so it was based on Unix. Those two operating systems have different APIs, right? So when they released OS X, this was a brand new OS with a new kernel with a different set of system calls. What does that mean for us? If you're a Mac user running OS 9 and they come out with their brand new operating system, OS 10, none of your apps worked. Because the operating system you were running yesterday had a different set of system calls. So all your programs would, at the very least, have to be recompiled to use the system calls for the new thing. But that was not as easy. It was harder than that. They had to do some pretty major updates because of the way OS X actually worked. So this implied that none of your old software would work. None of it. Yet Apple expected everybody to move over to OS X. Have we talked about what their solution was? What did Apple do to, because there was going to be a period of time. Let's say it was going to be 6 months. Just pull a number out of the hat. I think for some applications it was longer than that, but let's just say it's 6 months. There was going to be a 6-month period after the Apple people, Mac users, were running OS X before the companies that they had software with would release stuff that would run on that computer. So until you had an OS X version of Microsoft Office, for example, that type of thing. So what did they do? Did you just not do word processing on your Mac? So you keep the old version, just run OS 9, don't adopt OS X?
Yeah.
Could have done that. In fact, that probably would have been the smart thing. But most people did not do that. And any new Mac you bought would come with OS X on it. You were forced to run OS X. Now, OS X came with something called the Blue Box. Anybody heard of the Blue Box before? Blue Box is, we've heard of like VMware and stuff like that for you can run Windows on the Mac. The Blue Box was a virtual machine that ran OS 9. So you could run your old apps within OS X. Now on paper, to an uninformed person, you might say, oh, that sounds pretty good. But why is that a problem? Major performance issues. Because when you run a virtual machine on your computer, so if you have a Mac and you want to run Windows at the same time as you're running your Mac OS, so it runs Windows like it's an application, you're sharing your system resources. That's what it's kind of been our theme the last several classes is, how resource management with various tools in our computers. And now we're looking at a piece of software like a virtual machine that's going to say, okay, how much RAM do you want to dedicate to this guy? How much of your hard drive space do you want to dedicate to this guy? And keep in mind, this is way before solid state drives. So you didn't have speed. Okay, so a mechanical hard drive was a major drawback to running any virtual machines. So you ran this thing in the Blue Box. So you're running OS X. You basically have 0 applications that run in OS X. Like maybe like a web browser or something like that, maybe. So then you launch Blue Box and run all your programs through this virtual machine extra slow, right? instead of just keeping OS 9 on your machine, which is what people probably should have done. But this wasn't, most people aren't going to be the type that could just reinstall operating systems. That wasn't a comfortable thing for them to do. So in any case, you had we would just call this from our perspective a pretty major transition that Apple had just survived, right? They finally pushed their users onto a future, let's call it a future-proof operating system, or at least an operating system that gave them significantly better light at the end of the tunnel than OS 9 was giving them. And they had to survive that, let's call it 6 month to a year delay for enough software to be available for OS X for people to view it as a viable operating system for them to be productive. That's a risk. I mean, Apple could have just very easily said, look, we're going to stick with OS 9. And, even though it has its issues, at least your software runs. But they released OS X, and they announced to all the software developers way ahead of time before OS X came out about the conversion, and the conversion ended up being a lot more difficult for a lot of the software developers than they expected, and that's why there was a big delay. So Apple expected it to go more smoothly. They expected several applications to be ready to run on OS X the day it was released, and many, many, many were not. That was an issue, but Apple survived that. Then, like a couple of years later, maybe not even 2 years later, Apple switches to Intel. So they switch from a RISC instruction set, PowerPC, to Intel. Well, what does that mean? Well, so they had to port OS X to Intel. And this also meant that none of your OS X apps that were compiled for PowerPC-based OS X would run. So previously what they did is they switched the operating system. So you had a different set of system calls. Now they switched the architecture. Now the best thing to do would have been to do both of those things at the same time. If you're going to have a headache, have one headache, right? Apple didn't do that. They survived an asteroid. And then 2 years later, threw themselves in front of the train again by switching to Intel. Now, the funny thing is this actually ended up working. And I mean, I really think Apple's better for it today. I mean, Apple probably wouldn't be a company had those two things not have happened. Obviously, they had a couple of other things going for them, but they needed success from this in order for their success from all their stuff, iPods, iPads, all that stuff, to give them enough money to stay afloat. So we're kind of talking about two different pieces here that are meaningful to software. We're talking about compatibility. We care about architecture, or maybe we can think of it as an instruction set. Okay, that's really what architecture ends up meaning for us from a compatibility perspective. Underlying architecture could also mean how many registers do we have, an amount of onboard cache, that kind of stuff that might make within a same instruction set different performance levels, kind of i5 versus i7 processors, that kind of stuff. So architecture is the hardware itself. This is hardware. And then we have the operating system, maybe called the kernel. This is the software. Because when we're writing something for a particular operating system, all problems must be solved in terms of the system calls of that OS. Okay, and this goes beyond this. Whenever we're solving problems, we're always solving those problems in terms of the tools we have available to us. Right? This is in real life. This is outside of computers. Okay, if you have to fix something at the house and all you have is a roll of duct tape, you're going to fix it with duct tape. That's what you're going to do. All right? You got a bucket of tools around you, that's what you're going to use to solve your problem. So the operating system provides you an API, provides you a set of system calls, and you're going to have to solve all the problems with that set of system calls. All right? Now, the architecture, similarly, all problems must be solved in terms of the, as I referred to them, magic tricks provided by the CPU, provided by the architecture, provided by the instruction set. That's probably the better way of saying it. That make sense? Those are the two sides to the compatibility problem. Now, if you make the switch on both of those, then you only have to fight the fight once. Because you're having to re-implement code, recompile code. You'll just recompile. You're going to target a different architecture. So, for instance, when we're running GCC or something like that on my laptop, GCC has been compiled on here to, by default, target the architecture of my machine, which is the Intel architecture for Mac OS system calls. All right. But you can tell a compiler, you can tell it to use a different architecture. So you could compile software for a machine, well, on a machine that won't run on that machine by targeting a different architecture. So I could give the correct command line arguments here to GCC and say, I want to compile this program to run on MIPS processors or running on an ARM processor or something like that. And it would compile on this machine and convert it into those little magic tricks and stuff like that. It won't run on this computer unless I had an emulator that was emulating that instruction, that architecture, right? Emulating that instruction set. But I could do it because that's ultimately what a compiler is doing. And that's what we're kind of talking about in this next section. So we think about a compiler. At the high level, this guy converts high-level code into low-level code. Now, if we break that down, what is it actually doing? So this is taking our code that's written in C or C++ or Java, that kind of stuff, a high-level program, and turning it into assembly code for a particular architecture. That means an architecture that is either going to be Intel or it might be ARM. Let's just use those two because those are the two that we're kind of dealing with in here. So you're going to target one of those two architectures, but we're also marrying that with an OS. So we're targeting Intel or ARM architecture, and then we're targeting also within that an OS. So if we call this architecture, put it like that, and then we're targeting OSs. Let's call our common options for OSs might be Mac OS or Mac OS X, Windows, maybe it's Windows 10. Windows tends to be backwards compatible, but there is if you go and you look at a program, you know how it says on the side of the box, if that even exists really anymore, it says what's the minimum system requirements for a program? And if the program says Windows 10, for example, that won't run on Windows 7 unless they're lying, because it must use some new system call that was introduced in Windows 10 that did not exist in Windows 7. Okay, so Windows 10 is backwards compatible with Windows 7. So if you had a program whose minimum requirements was Windows 7, that program will run on Windows 10. But if you have a program that's minimum requirements is Windows 10, it will not run on Windows 7. That make sense?
Is that with Mac too? Would it be backward compatible with 99?
Definitely.
Okay.
Yeah. In fact, you'll sometimes find that you'll have kind of older, almost like shareware type programs that'll say that this works for because of when it came out. It'll say this requires iOS or OS 10.7 or higher, something like that. But then if you go and run it on 10.10, it'll run because that guy's backwards compatible with everything before that. Unless somewhere in the middle, they re-implemented some piece. There was a change. So, you could run into issues like that.
Well, I was gonna say, like, I mean, if you run into, at some point, isn't like one of the systems gonna be obsolete because they're not gonna be using all these commands? Because if they keep adding in more commands on like Windows 10 and Windows, I don't know, 11, 12, 13, whatever, Windows 13 is gonna have so many commands and it's gonna be a huge operating system. So they're gonna try and make those more like.
Yeah, you're right, but keep in mind there's kind of two things they're doing. They're not just always adding more commands. They're also improving existing commands.
Yeah, that's what I mean too. But even then, though, by improving it, maybe that's not necessarily going to speak to a program that ran.
Possibly, because these things are still. Think about them as functions.
Yeah.
So it's a magic trick that requires you to pass 3 pieces of information to it. So as long as they keep that the same. If it's still called the same and it still takes the same 3 kinds of information, but they totally change the way it works inside, that's not a problem, as long as it performs the same task, right? Now, it doesn't always do that. Sometimes they basically say this was not the right way of implementing this. In order to make this better, we have to change it. So then they have to decide, okay, well, do we keep the old version for backwards compatibility and then run the new version? Or sometimes what they'll do, if you've noticed in Windows, they have a thing called compatibility mode. So you can run a program like in Windows 7 compatibility mode. What it'll do is it'll do some almost like software translation for some of those things to almost like fake it, to make certain things still work that maybe won't run directly on the hardware. So, it's a real problem, but it's a problem that really is, it's only really seen when you're trying to run old software on very new operating systems or vice versa. New software on older operating systems.
Okay.
If you're kind of roughly keeping up with the Joneses,
Yeah.
you keep your software updated, you update your OSs, you're probably not going to have problems very often.
And then can you edit the OS? Like say there's one command that's getting caught on. Could you add in?
Well, it depends. If you are running Linux, certainly. It's an open source, I wouldn't say no problem. It's legal to do it. Yeah, so it's an open source operating system. You have full access to the code. You can go and change whatever you want and deal with whatever else you break. And then recompile it and run it. So you certainly can do that. Mac OS is not open source, and Windows is not open source. So you wouldn't be able to modify those. And I would say in general, that would not be something that would be very common to do, because that's kind of like a one-off fix. The better solution would be to get an updated version of the software that is made for that newer version. You'll have far less headaches. Something along those lines. All right. So what I want us to get out of this, what we've been talking about for the last little bit, is this idea that we have kind of 2 enemies of compatibility. We have a software level of compatibility and we have a hardware level of compatibility. And those 2 are different. They're different problems, but we have to target both of them. So I can write, for instance, I'm running this program, I'm running Keynote right now. And this program is running on the identical hardware as, well, let's see, how many of you have PowerPoint on your computer? PowerPoint, okay. Let's assume, I don't think I have PowerPoint installed in this right now. I have in the past. Let's assume I was running PowerPoint, okay? So he's got an Intel Core i5 or some processor in his laptop. I have a Core i7. They're both Intel architecture, whatever. Okay, so we both have Intel architecture stuff. And we're both running the same program. We're both running PowerPoint. So my program is targeting the identical architecture as his program, but it's targeting a different operating system. Because I'm running on a Mac OS X. He's running it on probably Windows 10. Yeah, Windows 7 on that one, whatever. Yeah, so we're in different operating systems. So his version of the program won't run on mine because it uses different system calls, even though the underlying architecture is the same. Does that make sense? And vice versa. All right. But if we were both running Windows machines and I was running an i7, he was running an i5, and even realistically, if I was running Windows 7 and he was running Windows 10, the same program would run on both. Windows 7 is new enough and popular enough that power points compatible with both. So we could have different operating systems and different CPUs, but in the same architecture family, and the same software would run on both. Does that make sense? All right, so we have kind of two enemies of that, and that's often something that's missed in computer architecture classes. So we focus so much on the hardware that we forget how important the software is for us. Now, way back when you had these giant computers that were the size of gymnasiums, all you had was the hardware. You didn't have an operating system. We've mentioned in here when we went through the Hello World program, right? How much work that operating system is doing for us. The operating system is a major power tool, but that comes with, what's the whole Superman with, great power comes great responsibility. So when you're going to choose to leverage that power tool, if you're going to use Windows 10, at that point you're agreeing to implement implement solutions in terms of the system calls that Windows 10 provides. Okay? Because at the high level programmer's perspective, as programmers, we live up here. We rarely, as programmers, think about the architecture because it's not our problem. That's the compiler's problem, right? We might think about the operating system we're on, okay? But even then, we might not even think about that much. Like, look, I'm going to write this. You might choose the tool that you're going to use depending on what operating system you're targeting. But at the end of the day, you're relying on your compiler to compile this for the right operating system and the right architecture that you're trying to target. That makes sense? So these aren't things that we really think about as a computer programmer, even though it's definitely something that's important that's happening under the hood. So the next question then is, how does a compiler work? Okay, so if I'm going to have, well, let's just talk about the high level. I think the book gives some examples of this, so I'll use the book's examples. We'll bounce back there in a second. But generally speaking, if you were what's the elevator pitch for how a compiler works? We already decided it's converting a high-level language to a low-level language. So now the question is how? Okay, so it's going to go through your high-level code, and we're going to look at, let's say we're doing Java. So we're looking at a line of code that says system.out.println something, or if we're doing C, it's printf. All right. So now we saw what the Hello World program looked like, correct? The assembly language program of that. So it's going to turn something like system.out.println or printf, Hello World, into those instructions, right? So it's going to have to figure out the equivalent logic associated with what that high-level command says it should do, right? So you're going to have this high-level command, printf, that's supposed to take some string as a parameter and spit it out to the screen. That way to decide what are the low-level language instructions for this architecture that are equivalent to that. And how can we leverage this particular operating system to make that job easier? Those two pieces. So we originally are mapping to those low-level instructions, which has a one-to-one relationship with the CPU. And we're also bringing in the knowledge of what's the underlying system calls for this operating system and creating functionally equivalent low-level magic trick calls based on your high-level lines of code. That's tough, right? Especially to write generically. You have to conceive upon. So, we've decided, if you want to think about it like this, we've decided we're going to build an engine, let's say, for a car. We all have kind of a general concept of what engines do. They make things go, right? That's what engines do. All right. Now, we might, depending on, whether or not you know anything about engines or not, you might have a concept of how they work under the hood. But at the end of the day, you know that if you have an engine here and you provide power to that engine and you hook up the right thing to the part of the engine that will drive stuff, it will make something go. Okay? It's not important what's happening on the inside. Some magic is occurring that's making something go up and down, right? Okay? But from our perspective there, it's not important what's happening on the inside. So we have this concept. That's the high-level programmer's concept. Like, oh, I need to solve this problem. I need an engine. Okay, so you're going to put the engine there. Okay, now that somebody had to build that engine. Okay, and that engine is actually implemented. You know, when we took the engine and put it in some, we'll use one of those small little electric engines. That way I can lift it. Okay, so we're gonna take the little engine. We're gonna put it right there. It's like I needed an engine, so I put an engine in there, and I hooked up the battery to it, and everybody's happy. But now some smart people had to make that engine. So inside that engine, we have a whole bunch of detail, right? A whole bunch of low-level code. Does that make sense? A whole bunch of individual instructions that make that engine work. Okay? I don't necessarily, as a programmer or as a car builder, let's say, have to know how that engine works because I'm going to go buy my engine from Honda or whoever makes the engines. All right, Mercury. But now I still appreciate the fact that inside that engine there's some detailed code. Now, are all engines the same? If you get an engine, let's say, I know a little bit more about boats than I do about car engines. So if I get a 75 horsepower engine from Honda, or I get a 75 horsepower engine from Mercury, those engines both are going to push out, probably within some sort of threshold, 75 horsepower, right? Now, are those engines identical inside with just a different company sticker on the outside? They probably have a lot of similarities, right? In fact, I'd be guessing at the percent, but they might even be 90% very similar. Okay, but different engines have a different approach. Like my understanding is Hondas are completely encased. So it's a sealed engine. You can't go in and really fix it. Where some of these other ones, you can open it up and do something with it. But whatever it is, they're both producing 75 horsepower. They have a different company sticker on the outside, but the instructions it took to solve that problem are not identical. So then when you talk to people at like boat shows or whatever, everybody thinks that their engine's the best engine, right? It's like, oh, I've never had a problem with a Honda. Then you talk to the guy over here and says, oh, don't buy those Hondas. Your boat will sink after 2 days. Yeah. Okay. But so which is the better compiler? Is Honda's approach of taking a engine, the idea of a 75 horsepower engine, and giving you their box with all their magic tricks put together in it, is that better, or is Mercury's better? Who knows, right? Everybody's going to have an opinion who cares about engines. The same thing's kind of true with compilers, right? If you have 3 different C compilers, they might not. Especially if they're not based on each other. GCC is a pretty popular compiler, so if somebody comes out with a newer compiler, it's entirely possible that they've based it on GCC because it's an open source project. But if we assume that we're dealing with, unrelated C compilers, it's very probable that those guys are going to produce different, functionally equivalent low-level code that may have different performance ramifications. Maybe certain aspects of, maybe this compiler produces code that's very fast under certain circumstances. That's, it's highly optimized for that type of stuff, but for something else, they've kind of like phoned it in, something like that. So we kind of get where this exists in the real world. So I'm not sure there's even a such thing as a best compiler. It all comes down to like adoption rate. GCC has been around for a while. It's been pretty highly adopted. I think you'd find a lot of people who would say GCC is the best compiler for C, but the original C compiler was called CC. GCC is the GNU version of CC. It's the open source version of that. CC was not open source. It existed before open source was a thing. But then you have alternate compilers. For instance, Microsoft Visual C++. They have their own compiler. Well, is there a pretty good chance that Microsoft Visual C++ is going to produce pretty optimized code for Windows, for Intel processors on Windows? That's probably a pretty fair guess. Where if you told GCC, because you can get GCC for Windows, you can download it, and you can use that as your compiler. I don't know the answer to this. I'd be guessing. But my suspicion is that the Visual C++ compiler that comes with Visual Studio probably produces more optimized code than GCC on Windows. That probably has very little to do with the quality of GCC. It has more to do with the fact that Microsoft knows how their operating system works under the hood, right? You know, they can decide where to take little shortcuts, right? You know, that's no different than in real life. Like you have a car. You know, I actually think about this. Edwin's roommate. His roommate, he's got a roommate named Amir, and we were going down to a hackathon. Last semester, and Amir was driving, and he was one of the people who brought a car, and his car wasn't overly reliable, kind of a junker, right? He since has junked it himself. He decided it's not worth fixing anymore. But his car has 4 seats, so somebody like me might say, "Oh, that could fit 4 people." Amir knew his car. So I could fit 3 people, including me. 4 people is going to be a problem. So the point is that he knew his car. Even though the car was meant to do something, he knew exactly how it was going to perform. And the most number of people you want to put in that vehicle is 3. And it made it there. You rode both ways in his car, didn't you? No, but you went to the hackathon.
Yeah.
You rode with him,
Yeah.
or did you ride with me?
No, I went to America.
Yeah, that would be terrible. Because he didn't have air conditioning either. Oh my gosh, it was so hot. It was like 95 that weekend. Oh man, so the students that went with me had all nice leather seats. I have rear air.
New compiler.
Yeah.
It's like certain things are like that online compiler is probably a newer one.
That's actually just a front end interface. It's probably running GCC.
I was wondering.
Yeah, so don't confuse the IDE. This is an IDE. So this is our text editor. What makes this an IDE is we have a text editor, we have a run button. Whether or not this online thing is a newer compiler or something like that, it very likely runs GCC behind the scenes. So I said, don't confuse the difference here. This guy here is not the compiler. This is a text editor with some run and debug buttons here. So I would call this an online IDE, integrated development environment. Under the hood, you have something that's actually compiling the code. In fact, there's a super high level chance it's GCC.
Because debugger is GDB, so
Okay.
like it should be GCC.
I mean, that's the one that's open source anyway, so they could use it. So they're using GCC. Probably most sites are going to use GCC. All right, but so the punchline here is that Visual Studio likely produces more optimized Windows code than a more generic compiler would because they know about their proprietary operating system. All right, and if they don't, then they don't produce better, more optimized code, then that's kind of shameful. Because they have all the tools they need to cheat the system, right? There's things that Microsoft engineers have put into Windows, they might have been duct tape, right? Where they happen to know that these 2 subsystems are connected to each other in a very, not the best way possible. Yet they know how they're connected, so they can take advantage of that, that little nuance. Kind of like Amir knew that if somebody sat in one of his seats, the car was going to die. It wasn't. So don't sit in that seat. It looks like a seat, not a seat. That's not a seat. All right. So yeah. So at the end of the day, the compiler is trying to target 2 different things: an architecture and an operating system. All right. So let me spend just a few more minutes here, and then we'll take a break. I at least want to start off with this instruction set thing at the top. So we're in 2.5. This is representing instructions. And so we're looking at what an instruction looks like. Again, they've introduced this thing called leg V8, which is a subset of ARM version 8. All right, get it? Leg and ARM, haha. So given that, the instruction space is a 32-bit space, right? 11 plus 5 plus 6 plus 5 plus 5 is 32. So that's 32 bits. What goes over here in the far left, this 11-bit space here, is our space for our instruction. So if we're kind of thinking about how the assembler actually works at the end of the day, we convert the low-level instruction, it looks English-like, add, into kind of its equivalent index. So this is instruction 1112. Does that make sense? All right. Or, so this is a decimal number. I'm presuming it's a decimal number. And then they're representing that as the hexadecimal equivalent, or the binary equivalent here. Okay? What does the instruction space here for the actual instruction, being 11 bits, what does that tell us about the instructions in ARM? What's the most number of instructions that ARM supports? Yeah, well, 2 to the 11th. Yeah, 2 to the 11th instruction. So 2 to the 11th instruction. So it supports 2,048 instructions. That's the number of unique instructions that I can have in ARM. That makes sense? That's a lot of instructions. It's not an infinite number of instructions. That's not a scary number, but it's a lot of instructions. That makes sense? So that is 11 ones.
It's 2 to the 10th or
2 to the 11th. Yeah, because it's all positive.
Oh,
Yeah, we don't have to think about sign numbers, because effectively what we're doing here is we have 2,048 total instructions we're allowed to address. That is 0 to 2,047, right? So this is instruction 0, this is instruction 1, this is instruction 2, so on and so forth. So we don't need negative, we don't need instruction -5. Okay, so we use the whole positive space to hold up to index up to 2,048 instructions. Now, I don't know, I doubt ARM uses all that space at this point. I don't know what their current number of instructions, here, let's just look it up real quick, since we're interested. How many instructions in ARM v8? I'm guessing 1,000 something. I was hoping somebody would just give it to me at the high level here. Well, let's see if this first one will just do we get a list of instructions? List of ARM v8 instructions. I just want a number. Did you find the number somewhere?
I saw it in
Oh, you saw it in here?
something in the course. See, but it says what? No, I thought it said the number.
Yeah, I don't see it yet. You would think that here. How many instructions in ARM? Let's go with that one. So this person's saying around 500 when you consider all the different operators. Oh well, all we can say for sure is it's less than 2,048, or equal to, less than or equal to 2,048 unique instructions. Probably far less than that to give it some room to grow, right?
So they don't have the serial order because the ad is like in 1,142.
It's possible they don't have them in serial order. It could be that they're grouped by like arithmetic instructions, things like that. So similar to like Unicode.
Some gap.
Yeah. Okay. So when we look at this space here, this tells us that we have up to 2,000 that ARM in this format. So this is the format of our instructions for ARM. So we write it like this: add x21, comma x20, comma x9. But that's going to get converted into this binary. This is the machine language version of this. That's what ultimately the compiler is going to, or the CPU is going to operate off of. Okay, so we write in high level converts it to this low level line. That low level line then gets converted into, here's the middle of that conversion, right? We convert add into its indexed value. So add is instruction 1112. X21, that is numeric register 21. This unused place is for shift space. We'll see that in a little bit. X20, that's register 20. X9, that's register 9. So then what they do is then we convert that to the binary and fill the spaces. So here's the 11-bit version of 1112. Here's the 5-bit version of 21. So with our registers, so this is register space, this is register space, this is register space. What's the most number of registers an ARM architecture can support?
An ARM?
2 to the 5th, right? 32 registers. Okay, so in the current architecture, ARM won't allow you to add any more registers because it already uses all 32. That's the most registers that physical registers you can have in the ARM instruction set without them changing this architecture, adding in an extra bit or something like that to the space, which would then make old programs not compatible. Because now your instruction size would no longer be 32 bits. It would be 34 bits or 35 bits. So if you added 1 bit per, if you gave yourself another power of 2 number of registers, you'd add 3 bits because these are all register space. This one, and this one. That makes sense? So now you'd have a 35-bit instruction space, which first of all would sound weird. Typically what they do is when 32 doesn't work, they just jump it to 64. It would be very weird to have a power of 35 or a 35-bit address space. Now, you might even say this. You might say, well, why is this 11 instead of 12 or 10 or 9 or something like that? Because chances are you can represent the number of instructions in less than 11 bits right now. Okay? Well, they've decided, okay, well, we have 32 registers, and that's what we're going to have. So these 3 buckets here are all registers. So we're just going to, that's 5 bits. Okay? This shift bit thing, they have to decide how much we're going to be able to multiply or divide by. So I'm not sure how they came up with the 6 bits for this, but let's assume that they had a good reason for it. Okay? So what do they have left? They have 11 bits. All right, we got to make all our instructions fit in there. That's the number of instructions we have, is to fit in 11 bits. So we have 2 to the 11th unique indexes for instructions. All right, does that make some sense?
Is this what it comes down to when they say 32 or 64?
It's related to that because that actually can mean several different things. So for instance, if they say you have a 64-bit operating system, Vista is a good example of this. So when Windows Vista first came out, you could have a 64-bit operating system, but it still had a 32-bit memory model initially, because you would have people who would have. Actually, hold on. Let me make sure I'm telling you this right. No, it's the other way around. The 32-bit version of Vista had a 16-bit memory model, because what you would have happen is, at that point in time, it was somewhat common for people to have 8 gigs of RAM. If you were running the 32-bit version of Windows Vista, it only showed 3.5 gigs of RAM, even if you had 8 gigs of RAM in there. Because it could only, there was half a gig that was reserved for the operating system. It could only show 4 gigs, but it showed 3.5 because half a gig is reserved by the operating system. So you had to run the 64-bit version of Vista in order to see all 8 gigs of your RAM. But the problem with that is at that particular time, there wasn't a lot of stuff that had already been ported over to 64-bit. So you would have had to run a lot of your stuff in 32-bit mode. So many people were not all that excited about installing the 64-bit version of Vista, although in order to get all their memory, in order to use all their memory, they needed to. Does that make sense?
Yeah.
And it goes the other way as well. So for a long time, the Mac operating system was 32 bits, yet they had a 64-bit memory space. They could address huge chunks of RAM, and that's kind of left over from the Unix operating system stuff, right? So, Unix historically has been a server-based operating system, and when you think about a server, you kind of think about a machine that has lots of hard drive space and lots of RAM, right? The instructions, it's not any more complicated from an instruction set perspective. Just it has a lot of RAM in it. So they needed a system to be able to address a lot of memory. So that just kind of came over by accident from just the Unix world, kind of the right tool for the job. But when somebody says something is 32-bit, it is related to that stuff, but you don't know which something is 32-bit. So saying an operating system is 32-bit doesn't automatically mean that every component of it is 32 bits.
Okay.
All right. So that's what we would call our instruction format. We talked about this machine language aspect there. Okay, so let's go ahead and let's take about a 10-minute break. And then we'll come back and we'll keep talking about the rest of this stuff and hopefully get far enough for me to give you the big surprise.